Radhe Radhe everyone. So yeah, today I'm having some glitches with my camera. Let me just check the audio, and if I feel that it is okay to go good with, then we can start with. Okay, we are live, right? You choose what you want and you like the most, and boom. Okay, moderators. No, I don't need moderators. Dude, these ads are like so much. Okay, I'm properly visible and audible. Let's start with today's video. There's some issues with the chat also. I can't pin it, okay, but not much of an issue. So let's start with today's first question. I woke up a little late. Okay, woke up a little late today, so took me time to do all the four questions. So let's start with the first question. Vowel consonant score. You're given a string S consisting of lowercase English letters, spaces, and digits. Let V be the number of vowels in it, and C be the number of consonants in it. A vowel is, you know what is a vowel, you know what is a consonant. The score of a string S is defined as floor of V by C, and if C is equal to 0, then the score is 0. So very simple question, V is equal to 0, C is equal to 0, and you go throughout all the characters in the string. If it's a vowel, then V plus plus. Otherwise, if it's an alphabet, then it's obviously a consonant. So C plus plus, and then we return if C is equal to 0. Question if C is equal to 0, then it's a 0. Otherwise, it's a V by C. Okay. I don't think there will be any doubt on this question because this was quite simple. Let's move on to the next question. The second question is maximum capacity within budget. You're given two integer arrays, cost and capacity, both of length n. The cost of I represents the purchase cost of ith machine, and capacity I represents the performance capacity. You're also given an integer budget. You may select at most two distinct machines such that the total cost of the selected machine is strictly less than budget. Return the maximum achievable total capacity of selected machines. So it basically tells you that you have two arrays. Okay. One is the cost array, the other is the budget array. Okay. I'm having a feeling that I'll start uploading videos without face cam because it's quite low effort to do that already. Okay. So let's say this is a cost array and this is a capacity array. Okay, so you have to maximize the capacity. Okay, you can choose any two cost, and you have to choose the cost in such a way that the sum of the it's not actually any two also. It is like you can choose one also, you can choose two also. Okay, but choosing one cost, it is very simple. So I'm talking about only the two case because it was given in the question that you can choose at most two distinct machines. Okay, so the total cost of the selected machine is strictly less than budget. So remember one thing, it's strictly less. Okay, so you know the cost of them. So what you can do is, first of all, you can have a one-way array. Okay, going through this, and for every specific element, check if the cost of it is less than budget or not. If it is less than budget, then we can have this capacity. Okay, if it is less than budget, we can have this capacity. But if it is not less than this budget, then we can't have this capacity, right? Then we can't have this capacity. So similarly, you can get the one pass method. That is for it, since it was given it is at most two, so you have got it for one. Okay, you got it for one machine. Now you have to choose the other machine. Now how to choose the other machine? It's a very greedy way to do it. There is a very greedy way to do it. What you can do is you can obviously merge both the arrays. Okay, let me merge both the arrays. Okay, now that the arrays are merged, what you can do is you can sort them. Okay, you can sort them on the basis of their cost. You can sort them on the basis of their cost, right? Now the moment you have got the cost, let's say now this is cost is sorted, right? So let's say it is like 1, 2, 4, 5 and 7, right? And you are pointing at currently 1, and your budget is, let's say, 10. Okay, so what you can get 9 minus 1, right? You can get 9 minus 1. Why not 10 minus 1? Because 10, it should be strictly less than that. So you can get 8. The cost of the second machine can be at most 8. Okay, right? It can be at most 8. So all of the elements are 8 or less than 8. So you can take all of the elements. Now let's say I'm at 2. So it will be 9 minus 2. That is 7. So I can take all the elements with 7 or less than that. That is all these elements. Now let's say I'm at 4. Now this is a tricky question, tricky condition. 9 minus 4 is 5. Okay. So for this 4, you can only take this 5. Okay. Now for all these windows that I am drawing over here. Okay, all these windows that I am drawing over here. This one, and this one. Can you find out anyhow what is the corresponding maximum capacity for those windows? Because we are in a greedy way, right? So let's say if we are considering 1. So we will take this capacity plus the maximum of all these capacities. Let's say we are taking 2. Then let me use a separate color for that. We will be taking this capacity and the maximum of the window, that is this one, maximum of this. Okay. Now let's say we are taking 4. Okay, we are taking 4. So what we will be taking? We'll be taking this capacity and the maximum of this window, that is this one. Right? You're getting it? So this is the basic design of the problem. I hope I'm audible with you guys. Yeah, I'm audible. So this is the basic design of the whole problem. Okay. Now the main challenge of this is, when I'm talking that you have to find the maximum of this window or the maximum of this window for the capacity array, are you going to traverse through all the elements and you get the capacity out of it? That is not a good thing to do, right? That is not at all a good thing to do. But you know what? Like, what you can do is you have to think of a data structure which will give you the maximum value in the specific sliding window. Okay. I mean, not sliding window, it's like a different type of window, whatever you may call it. Let's say it's a shrinking window, because earlier it was like this. So it was shrinking only, right? The window is shrinking. This is one thing that you can notice. Since we have sorted the array, so the window is always shrinking. First of all, the window was like this. Then it shrank to this. Then it became like this, right? So the window is always shrinking because the array is sorted. So can you think of any data structure which can make it more easy for us to compute the maximum, instead of having a big O of the sliding window, like instead of traversing throughout the whole sliding window? Because why would you traverse throughout the whole sliding window? You know, like this is the maximum. So what you can do is, you know that this is the maximum, and whatever is the maximum of this and whatever is the maximum of this is going to be the maximum for this, right? So you know this, right? You can backtrack it. For this also the same thing, the maximum of this and maximum of this and this. So you can backtrack the same thing. But we need a data structure which will make our job a little bit easy for us. Obviously, there is no data structure which can provide this in big O1. Okay. But yeah, big O login, there are various data structures that you can use. One is a segment tree, which I won't prefer you to use at this point, because this is a very easy question and doesn't need that hard data structures to use. So we will be using a priority queue, or as you may call it, a heap. Okay. What is the heap? The heap is of type max, because you need the max element, right? Now, how are we going to utilize this heap? Okay. See, I know that in the heap, I can go on putting elements, okay. But whenever I'm choosing a sliding window, okay, let's say, so when it's not a sliding window, this is actually like slipping out from my tongue. Whenever I'm choosing a shrinking window, let's say for this window there were some elements, but now we have to remove all the elements over here and all the elements over here, right? But a priority queue will always eliminate the maximum element, right? The maximum element. It doesn't care about which index you were. So in the priority queue, what we can do is, we are not going to simply take an integer value. We are going to take an array, or rather a pair, whatever you may call it, where the first position you can set it as I, that is a position, And the second position you can set it as cap of I. Okay, now you know that this is a capacity of I. Great. Now the moment you are at this, let's say you are at this position, okay, you are at this position where you are going to find the maximum of this. What you can do is the priority queue is going to be sorted on the basis of the capacity I. Remember one thing, okay. If you want it to be more easy for you to understand, I think this is a way that we can do it in Java, but in C++ it automatically makes it like this, right? So if I make it like cap of I, then you don't even have to mention any comparator. If I make it cap of I and I, then you don't even need any comparator, right? So you can do it like this. Now see, let's have the priority queue. Let's have the priority queue. So in this priority queue, what will happen? All these elements will be there, right? Now let's say you're popping an element and it is a maximum element, but this maximum element is over here. The moment you pop this element, from this index, you can find it out whether it is lying in the range that you want or not. If it is not lying, pop it up. We don't need it. We don't need it further also because the window is shrinking. If it was not needed in its earlier state, it will be not needed in its later state also. Okay, because the window is shrinking. And if it is in this range, then add it to the answer. Okay, it will be better if I take an example out of this. Let me take an example out of this. Let me use which one should I use? Let me use this one only. Okay, 48531527. See, I am directly sorting it out. Okay, I am not going for like one by one. I'm directly sorting it out. That is, I need to sort it out on the basis of cost, right? So it is going to be 3, 4, 5, 8. Correct? Now I have capacity 1527. So for 3 it is 7. For 4 it is 1. For 5 it is 2. And for 8 it is 5. Okay? This is cost. And this is capacity. We have a priority queue. Initially in the priority queue we push everything. Okay? We push everything. Because we don't know what to take. So we'll push everything. So let's say it is going to be pushed like 7,1. Right? Sorry, not 1, 0, right? The index is 0. Then there's 1,1. What is this 1,1? 1 is the capacity of I and this is the I, that is the index. Then you can have 2,2. Then you can have 5,3. Correct? So we have pushed everything to the priority queue. Now this is a priority queue, right? So initially, let's say I'm having a 2-pointer. I'm having 2 pointers. Array, yaar. 7, 7, 7. I'm having 2 pointers. One is pointing as I, the other is pointing as J, right? What is our target? Target is 8. So we find out 3 plus 8. What is 3 plus 8? It is 8, 9, 11. 11, right? It is greater than equal to 8, right? It is greater than equal to 8. So we can't take this. So we push J to this pointer. 5 plus 3, 5, 6, 7, 8. 8. It is still greater than equal to 8. We can't even take this. We put it far away over here. Now it is 3 plus 4, 4, 5, 7. Right? 7. Is it greater than equal to 8? No. So we are okay to go with it. Correct? So we are okay to go with it. Now that we know that I is at this position and J is at this position, so we need the maximum of this window. Right? Maximum of this window. So we start popping it out. The first pop is 7 comma 0, right? Because that is the highest value. But is 7 comma 0 in this range, that is from 1 to 1? No, this 0, not in 1 to 1 range. Then we pop up the next element, that is 5 comma 3. This 3 is not in range of 1 comma 1. Then we pop out 2 comma 2, still not in range. Then we pop out 1 comma 1, and it's now in range. Okay, it's now in range. So we get 1, and over here we had a capacity of 7. So 7 plus 1, that is 8. So our answer is going to be 8, if I'm not wrong. Correct? Yeah, the answer is going to be 8. If you want, you can do with various other examples also, and this is the basic idea of this. Now let's say, actually I have covered all the edge cases, so I won't be covering anything else. So I'll just directly go with the code. The code, and what I'm doing is I'm merging both the arrays, cost and capacity. I'm sorting them on the basis of their cost. Then I'm taking just for single digits. That is, if I'm taking only one capacity. Okay, it may have also happened that let's say there was a 7 over here. Okay, there was a 7 over here, and the value of it was 99, right? So in that case, I will be over here, right? But there won't be any j, right? There won't be any j. J would be over here, because for 7, 7 plus anything is greater than equal to 8. Okay, other than 0, and there is no 0 possible. So it is a very simple thing to say that in that case you will be having 99. So what you can do is you can have a one-way traversal throughout the whole array and check if the specific element is less than budget, then you can take this as a maximum. Okay, so that is what I am doing. If x of 0 is less than budget, answer is equal to mat.max, answer comma x comma 1. Else we can break. Why are we breaking directly? Because we know that the array is now sorted, right? If at any position, let's say at this position 8, now it is 8 is greater than equal to 8, right? Now at after this, elements can be of like 9, 10, 8, all these elements are going to come, right? So they will also not be satisfying. So we can directly break it out. So that is the reason I'm breaking it out. Then I'm taking a priority queue. I'm taking it of size int. I'm taking it of type integer array. You can take it of your own data structure also. You can make a pair out of it. But I was in a hurry, so I took this. You can save a little bit of space, but not much. Space and time also, but not much. So I is equal to 0, I less than n. So I'm putting all the elements into the priority queue. Okay. Now you will realize, you will see one thing, that I am doing I comma AR of I of 1. That is, I am putting the index first, then the then the capacity, right? But in C++, I think if you put the element first and then the index, you don't even need to verify. You don't even need to use this comparator. Okay, you don't even need this lambda. But since I'm using a lambda, so I'm putting it in the way that I feel to be more confident. So I is pointing at the first element, j at the last element. While I is less than equal to j, we check if adding I and j is less than budget, then it's a possible thing. Otherwise, j minus minus. I just told you that j minus minus. And yeah, one more thing, that is I also gets plus plus. Okay, I also gets plus plus. So if a of j, this is less than budget, so it's a valid thing. I take the maximum. And what is the maximum? The maximum is nothing but the maximum of the priority queue, right? The maximum of the priority queue. Now, what I do is first of all I pop the elements which are not in our range. Our range is what? What is our range? Our range is I plus 1 comma g, right? All the elements in this range I will take. All the elements that are not in this range is going to be either less than equal to I or greater than j, which I won't take. Okay, so if the elements are at this positions which is not acceptable, I can remove them. Okay, and at the end I find out if the priority queue is empty or not. Okay, if the priority queue is empty, you take 0. If it is not empty, you take the top element, that is a maximum element, and then answer is maximum of answer comma AR of I of 1, that is the capacity of the ith element, plus the maximum of the window. Okay, and once you're done with this, so you know that you have got the capacity for I. Okay, so you move on to the next I, and you go on doing this and you return the answer. I thought it can be solved by greedy. Didn't even realize this can turn this hard. It appeared like knapsack. Yeah, it was greedy only. This was a priority queue thing, so it was quite greedy only. Yeah, that's it. By the way, hi Abhay, how you doing? Today I'm having some issues with my screen, so I have put off my camera, and I think the stream quality is also improved because of this. So I'm deciding that I may turn off my camera from the next time. You can see that there is drop frame of 0, so I think I'll turn off my camera from next time. It's better for me to stream. Okay, let's move on to the next question. Design auction system. Okay, design auction system. You're asked to design an auction system that manages bids from multiple users in real time. Each bid is associated with a user ID, item ID, and bid amount. There's auction system. So this is basically a kind of LLD type of question. Okay. Add bid, what it does is it adds a bid in the name of the user ID on item ID with the bid amount, bid amount. Update bid, what it does is it's the same thing as add bid, but it updates. Okay. So this is basically, this is the post request and this is the put request. Okay. And this is the delete request and this is the get request. So it is basically very much like you are designing an API. Okay. And you have to do it in a very good way. So it's really nice to see that LeetCode is coming up with such great LLD type questions, because in this, like if you know about API designing, basic API design, it's basically all about CRUD, right? So this is the create, this is the update, this is the read, this is the read, and this is the remove, delete. Okay, and this read is also a little bit twisted. Okay, not a simple read that you can do it with whatever data structure you want. So if you talk about the system of bidding system, auction system, you have to do it in minimum complexity, and it is given that user ID and item ID is 5 into 10 to the 4, which means that every specific bid, you are removing it, you are adding it, you are updating it, whatever you are doing it, it has to be in log n. Okay, because overall complexity will be big O n log n. From the constant we can get it out. Now that user ID and item ID, so this we know this. Okay, so how are we going to develop it? We are going to have two maps, bid map and item bid map. Okay, what is a bid map going to have? The bid map is going to have for every item ID the users. Okay, and the item bid is also similar. So initially we initialize bid map and item bid. Okay, and you know what a bid is? A bid consists of a user ID and an amount, right? There are three things in a bid, right? User ID, item, and bid amount. But why don't we keep the item? Because the item is part of this. Item is part of this. So we need this only or this only, right? These two are integers, which is okay with us. So it is going to be item ID, uh, what to say, bid amount and the user ID. Okay. So this is a complex map. Bid map is a complex map, but this map is a very simple map. You show all the bits for a specific item, and whenever you're going to return, you're going to return the maximum bit that is there. Very simple to understand. I'm not explaining it using Excalibur because this is not much of a visualization problem. This is a more of a LLD question. Now, if there is you're adding a bid, okay, in the name of the user ID and the item ID and bid amount. So first of all, in the bid map, you have to put, if it is not there, if item ID is not there, you have to put a new map for it. Okay, the moment you have put a new map for it, then there is a item bids also, right? So in that also you put a map for it, item ID, and if the map is not there, then you have to initialize it. How are we initializing the tree set? The tree set is basically if you're taking two elements and their amount is the same, then I'll return the user with the higher user ID. But if the amount is different, I'll return the user with the higher bid first. Okay. Why do we do this? Because it was written returns the user ID of the highest bidder for item ID. If multiple users have same highest bid amount, return the user with the highest user ID. Okay. So this is the reason why we are doing this. Now we are going to replace existing bid if it is present, because we are adding a bid. So we have to also check if there is a bid already present, right? Because it was also given if same user ID already has a bid on item ID, replace it with a new bid amount. So we in the bid map we check for item ID. Sorry, sorry, my mistake. We check for item ID and then we check if the user ID has an item ID for that or not. If it has, then we go and call remove bid. Okay, we call remove bid of user ID and item ID. Okay, now let's not go deep into this at this moment. We know that we have already removed it. Now we are going to add it. That is, in the bid map we add item ID, user ID, bid amount, and in the item bid we add item ID, user ID, bid amount. Okay, very simple. I hope there is no doubt regarding this. Now let's go to the update bid. Now update bid is also very similar to whatever we did in earlier. Okay, that is, we know there is an old amount, that is bidmap.get item ID.get user ID. Okay, so what we do is we get the item ID and remove that bid. Okay, and then in the bid map we put the new ID, sorry, the new bid, okay, for that item ID, and in the item ID we add the new bid with the new amount. Okay, very simple, no issues. Now let's go into the remove bid, user ID and item ID. What do? We go to the bid map, we get the item ID, we get the user ID. So now we have the amount. Okay, now we remove that from bid map. Okay, we know the older amount, we remove it. Now what we do is item bid, from that we remove the user ID and amount. Now remember one thing, whenever you're removing anything from the map, it is better to keep an object of it. Okay, because in case of any other things, if you're not wrapping it with some object, it considers it as a separate object, and the comparison of it is done on the basis of objects. So always try to make a different data structure, like a different class like bid. Don't use blindly integers arrays for this. Okay, like if I would have liked to, in the as in the previous question, I would have done like this, right? I would have done like this, but that would be a problem because it will be creating a separate object of that, and the comparison won't be working that good. Now for get highest bidder, what we are going to do is you are going to check if item bid doesn't contain item ID, or if item bid contains item ID but it is empty, that is all the bidders have removed the bids, then return -1. Otherwise, simply item bids.get item ID, get the first one and the user ID. Okay, dot first is, what is dot first? Item bids.get item bids, item bids, item bids, item bids. Okay, dot get, you get the tree set, and tree set dot first gives you the maximum, and then you return the user ID for that. Okay, I hope this is not having any issues. This is an accepted solution. If you want to see, there is an accepted solution. I submitted at 9:44. Now there may be some ways to optimize it, but I think this is well optimized. Okay, let's move on to the last question. No doubts, great. The last question is lexicographically smallest string after deleting duplicate characters. You're given a string S that consists of lowercase English letters. You can perform the following operation any number of times. Choose any letter that appears at least twice in the current string and delete any one occurrence. Return the lexicographically smallest resulting string that can be formed this way. A string A is lexicographically smaller than a string B. You know when it is smaller. So you can remove elements if there is at least two occurrence of it in the string. This is very similar to a question where you have to find the smallest, the lexicographically smallest uh, sequence of string subsequence of size k. There is a problem like this in GFG, I think. I think even LeetCode has it, but I don't remember. I remember solving it in GFG. So over there we use a stack. You know what is the main use of this stack? Why we use a stack? Let's say we are having A, B, C. Now we can remove this A, right? If we remove this A, this becomes A, B, C, right? If we remove this A, then also it becomes ABC. If we remove this B, it becomes A, C. If we remove this C, this becomes A, B. Which is the smallest? The smallest is AAB, right? But how do we determine this, that this is the smallest? Okay, that is the most important thing. Now, in what happens in this thing is, in this K thing, it is not given that you have to have a size of K. You can have a size of less than K also, right? In this question, right? It doesn't restrict us to any size. So if we are going to consider only one removal, we can remove this also. We can make it AB also, right? We can further remove this. But how are we removing it so that it is going to be lesser than this? Because our target is not to find the least. We are going to go one by one. That I want something which is lesser than this, then something which is lesser than this, and so on, right? Now the point is, let's say if you're having this AABC and ABC, you can see one thing. This is not a valid thing. Okay, this is not valid, right? So basically, no matter whatever you remove from AABC, it will never be the smallest. Even AAB is not the actual answer, because you have to keep at least one occurrence of B, right? So AABC is not the answer. So let's take a real life example, that is this one, AACCB. And the moment I put it up, you'll notice a pattern. If you have already noticed it, it's great. See, I have AACCB, so I can remove A and C. I know, okay, I can remove one A and one C. Now, is it a good idea to remove a A? Right? We have to think, is it a good idea to remove an A? Nope, it is not a good idea, because if you are keeping a A, the next element will be C, right? And these two, the difference, this C is greater, right? So we are not going to remove it. But we remove C. Why do we remove C? Because if we are removing C, then C gets compared to this B. Okay, C gets compared to this B. And comparing this C to B, so if I'm putting this B, so this B comes over here. See, if C comes over here, it is not a good thing. It is going to increase it. But if B comes over here, it is going to decrease it. So it's a good thing to do. So I can remove this. Now how are we going to do this? We can use a simple stack. Put A in it, done. Put another A in it, done. You have C. Is C greater than A? Yeah, it is greater than A. So we don't need to pop out. Again, there is a C. Is C greater than C? Nope. Don't need to pop out. Sorry, yes. Greater than equal to, so we don't need to pop out. Now we have a B, right? But there are elements which are lesser than B. Sorry, which are greater than B. So we can pop them out. We can pop this C. We can even pop this C out, but we don't have the liability to do that. We don't have the permission to do that, because we need at least one C in the array. So we pop out the C that is at this utmost position, and then we push in B. So what is the answer? AACB. Okay. Now let's say there was AACCBB AAA. right? This could also be a condition, or rather, let's say not like this. Let's say there was BB. Okay, BB. Now there is another B. Now it will be coming on top of it. But you know that we can remove occurrences, right? We can remove occurrences. So the last B we can remove it. But according to whatever we have done, we have not removed the last B. So at the end, what you can do is you can go on removing elements from the extreme top. Okay, until and unless you find that there is at least another element present in the array. Sorry, present in the string that is in the remaining part of the stack. So you can remove this B. But the moment you come to this B, you can't remove it because there is only one B. Okay, so the answer is AACB. AACB. Okay, Z. Z. Let me go through the solution. I meant a stack, but I'm using a DQ. I'll let you know why. Because the moment you are done with the stack, now the moment you have to return the answer, you know what the stack does? It pops out from the top, right? So whatever we are going to get is nothing but the reverse of the string. So we have to do twice operations. That is, we have to reverse the string. Sorry, we have to pop the whole stack and then again reverse the string. But why would we do that if we can use an array DQ? Okay, a frequency array. For all the characters in string, I'm going to increase its frequency. For all the characters in the string, I'm going to check if the stack is empty. It's not empty. Okay. Is the frequency of that greater than 1? That is, there is one element safely present in the stack apart from this. Okay. If there is one element already safely present in the stack, or rather not in the stack, in the whole string, if there is at least one element, okay, apart from this, then we are also going to check if ch is less than st.p, because this is the main condition of the pop, right? We are only going to pop it if the current character is lesser than the top of the stack. So if it is so, we are going to reduce one frequency of it and we are going to pop the top of the stack from it. Okay, we are done with it. We are going to push the current character to it. This is it. Nothing much. This is it. You are done with it. Now you have to. I'm building a string builder because if I would have used a string st directly, then it will be big O n squared. Okay, because Java doesn't support in place for strings because it has a separate string pool for it. So it is a little bit time consuming, a little bit complex on the basis of time. So we are not going to use that. Now while stack is empty and the top of the frequency is still greater than 1, that means there is still one element which will be remaining if I pop it out. Then do nothing but pop it out. Why would we keep it, right? If we can pop it out, pop it out. So we are popping it out. And then while st is not empty, we are going to append poll last. Okay, this you can see that I'm not going to pop it out. I'm going to poll the last of it. And poll last does nothing but it gets the last element, the bottom of the stack, and then pops it out. Okay. So you're done with it and return answer.string. This is an accepted solution. If you want to see, it's an accepted solution. Okay. So yeah, that's it. That's it from my end. It was a brilliant stream. Let's rate the problems. Unpopular opinion, but I think C was a little bit harder than D. Okay, no issues. This has become green actually. Medium, hard. First question was easy, I remember. It was very simple, vowel and consonant. But I got a bug on that. Because I didn't read the question properly. I started solving, I'll just show you, okay. I started solving from 9. Okay, this much of code you will realize that I'll take hardly 1 minute to write. So I started solving from 9. This question I did at 9:39, 9:44. So I did it in 44 minutes. I would have done a AK today if I was giving the contest, but I woke up late. Okay, not an issue basically. So the first question was easy. Second question was little bit of like priority queue and stuff. It was medium, man. I have to rate it medium. Let me do one thing, man. I'm having some OCD issues. I don't want. I want to make this okay. So second question was it was a good question, man. I think I should give it a medium question. I could have also given it over here, but I think it's okay to keep it over here because this C it is going to come on that position. Okay, sorry, this D is going to come at this position, and C comes at this position. C was hard, man. C was like getting all the data structures and considering that it is a LLD question, so it's a good question. So yeah, this is the final rating for it. If you want, what I want to do is I'm not going to put M over here. I'm going to put M over here. Okay, easy, medium, and this is a little bit of harder end of medium. There is a sorry, I meant the opposite thing. This is a harder way of medium, and this is a medium way of harder. Okay, so yeah, that's the rating A B C D. So yeah, thank you guys for joining. Whoever joined, thank you guys for joining. That's it from my end. I'll meet you guys next week with another stream. Till then, goodbye.